Okay, let me talk about the magnetic mirror. That's one signature applications of first adiabatic invariant magnetic moment nu. Sorry, mu. So the setup is pretty much just like this. The white line is a magnetic field line. It's stronger on the both sides. The middle has a weaker magnetic field. If you put a particle here, then the part of the particle, some portion of particle will be stay confined within this region. So let's calculate it to see the reason why. As we know that if the time variation of magnetic field or location variation of magnetic field in terms of Lamar radius or cyclotron frequency is small, then we can use this. We can assume that the mu mv square over 2b is a constant, is an invariant. So that means at anywhere mv square over 2b equals to any the other place. As we know, that's what the definition of invariant is. And we can assume that where the magnetic field reaches the maximum, which is this area, the V parallel reaches to the maximum. So we can think that it just keeps generating faster, but due to the conservation of energy, the parallel kinetic energy will keep reducing until all the kinetic energy goes to the perpendicular direction. So we using this, we have this. V parallel square over V parallel square max equals to B over B max. Since V parallel equals to V parallel square equals to V max square, V per square max. As the argument that I made, basically when this becomes a maximum, then there should not be any parallel direction if it's confined. Basically, reach to here, then the parallel kinetic energy should go to 0. So when I'm having this, does this become V per plus V parallel here, and then that becomes sine theta square equals to B over B max. And also we define the mirror ratio, Rm. It's mirror ratio that's equal to 1 over Rm. That's just the definition. And what does it mean? That means within this angle, it's not necessarily to be the center, just so no. It could be anywhere that the magnetic field here. I just draw this symmetrically because it looks nicer in that way. So there's a B field here, and then if we go, here's a loss cone, basically that's a theta here. So anything within the cone, the particle will end up losing. As you can see, the middle definitely will lose because it just follow the magnetic field line, and it just get lost. But outside of the cone, then the particle will be confined, like this. So that's basically what magnetic mirror does. So the energy aspect of this picture is relatively easy to be understood, but if you still have a hard time to have a firm grasp of this concept, I can provide a different perspective. You can think this into in the sense of Lenz's law. So pretty much it means if you see the particle is moving, so it's kind of like a little coil. As it going to the higher magnetic field line, it will try to induce a current such that the magnetic try to resist the increase of the magnetic field, and it ended up become faster and faster. Then that means pretty much the vertical kinetic energy keep increasing until there's no perpendicular kinetic energy, then they will just go back. And another thing you can think of is a mirror force. So it's kind of basically the analytical understanding of the Lenz's law. Basically, that the force will be the magnetic moment dotted by the gradient of magnetic field. So yeah.